Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am one of the co-founders here, along with my younger brother, AJ Raj. As you can see today, we're going to be continuing and actually concluding our logarithmic functions mini-series in our Algebra 2 course. Today, our whole focus is going to be on some practice problems that you can anticipate seeing on assessments that you'll have in your Algebra 2 class the teacher will give you. In this lesson, our objective is to breeze through a few practice problems. If you've done your practice, these really should be easy, and I'm just going to be covering the skills that we've discussed in the past few videos. I'm just going to be going over those and how we're going to apply them to any practice problem that we are given. So these practice problems are going to be covering graphing. The first one's going to be on graphing specifically. The second one's going to be on translations. The third one is going to be rewriting a logarithmic function in exponential form, just reviewing. That's something we discussed in one of the first episodes. Then we're going to be looking at inverses, and then the last one's going to be a special case, and all of these are going to be focused on the logarithmic function family that we've been learning about. Before I get into this video, I'd really appreciate it if you all could like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. So let's jump right into the video. The first problem, like I said, is going to be on graphing. So here's the problem. We're given these two functions and we're asked to graph them. So we're told graph the functions y equals log base 2 of x and y equals 2 to the power of x. That's an exponential function. We're doing this on the same set of axes. So we're not doing two separate graphs. We have one x-axis and y-axis. So we have one coordinate plane, and we're graphing both of these functions on the same coordinate plane. So I'm not going to be working through this problem hands-on with you. We're really just trying to breeze through some problems in this video and keep it brief. So I'm just going to be talking about the solution, which you can see up here. The first thing we're going to do is we are going to take our logarithmic function and we're just going to write it y equals log base 2 of x over here. Then in order to graph this, we have to make an xy table. As you can see, I've already written up the xy table. Also, you can see that there are no translations, so there's no minus h or plus k added to the end. This can be seen as a parent function. It's pretty straightforward. If you see a parent function, what you can do is you can just take y coordinates and then you can just pretty much base them around the origin, which is 0. As you can see, I picked -2, -1, 0, 1, and 2, as you've seen that I've picked in previous videos in all of those problems we've done before. Afterwards, you want to rewrite this in exponential form, which I didn't do, but it should be pretty straightforward. When you rewrite in exponential form, this would come out being x is equal to the 2 to the power of y, because it's the opposite of it's the opposite of the inverse, which is exponential form. Even though we're writing the log in exponential form, it's not going to be the same as exponential form, because in exponential form, the exponent is x. In this case, we've switched the positions of x and y, so that's why we're actually going to be plugging in for y and getting x out. We're going to plug in for -2, 2 to the power of -2 is equal to 1/4, 2 to the power of -1 is equal to 1/2, 2 to the power of 0 is 1, 2 to the power of 1 is 2, and 2 to the power of 2 is 4. That's how we found out our x coordinates, and then we also found out what the asymptote was going to be. With logarithmic functions, we have a vertical asymptote, and because this is a parent log, that vertical asymptote is going to be x equals 0, or the y-axis, because there's no translations at all. So let's look at the second function, which is y equals 2 to the power x, which is an exponential function. Hopefully you can realize that. It's actually the inverse of the log function we just looked at. And when we graph, you'll see exactly how it's the inverse. You'll also see it in the xy table we made. If you look at this xy table, the x coordinates of the exponential function were actually the y coordinates of the log function, and the y coordinates of the exponential function were actually the x coordinates of the log function. When we swap the input and output of a function, we're actually finding its inverse. So the inverse of the log function we found is this exponential function. For any exponential function, we actually plug in for x instead of y like we did with log functions. So we can pick 5 points centered around the origin. I picked -2, -1, 0, 1, and 2. And if we plug these in, 2 to the power of -2 is 1/4, 2 to the power of -1 is 1/2, 2 to the power of 0 is 1, 2 to the power of 1 is 2, and 2 to the power of 2 is 4. So it's pretty much just swapping the x and y coordinates we just found. And exponential functions have horizontal asymptotes. Because this exponential function doesn't have any kind of translation, The horizontal asymptote is going to be the x-axis, which can be written as y equals 0. Then when we plot these points, as you can see here, we plotted 5 points for the log function, which is this curve that I'm tracing with a laser right now. You can see that this is also the asymptote, the y-axis of the log function. And then you can see the exponential function plotted here along this curve that I'm tracing. And then the asymptote is the x-axis, which I'm also tracing right now. You can see that they're reflected across the line y equals x. When they're reflected across this axis of symmetry, it means that they're inverses, which is pretty much what I was trying to show you in this problem. So that's problem number 1. Let's move on to problem number 2, which is on translations. So here's the problem. Describe how the graph of y equals log base 3 of x minus 5 plus 3 compares with the graph of the parent function y equals log base 3 of x. In order to compare, we're asked to graph the problem, and then we're going to identify the domain and range. So here's the solution. What we always do when we have these translations, when we get a log function ever, we're going to identify are there translations or not. If there are not, then it's a parent function, and it's pretty straightforward for graphing it. We would just rewrite it in exponential form, x equals some base to the power of y, and we make our xy table, and then we graph. However, we have to see if there's any h factors or k factors. In this case, there are. Remember, the formula that we learned was y equals a log base b of x minus h plus k on the outside. That was like your translation formula. In this case, our h is 5 and our k is 3. Our h is positive 5 because there's a minus 5 in the set of parentheses. If this was a plus 5, then our h would be negative 5 because there's always a negative sign in the parentheses. If we have a negative h, then negative times negative is positive, but in this case our h is negative in the parentheses, so that means it's actually a positive number. So it's like a flip-flop. You can think of it that way. And then our plus 3 is our k, so it's pretty straightforward. H, remember, moves our graph to the right or to the left, so horizontally along the x-axis. And then k moves our graph up or down along the y-axis, so vertically. So what we're going to do first is we're going to take the parent function, which is y equals log base 3 of x, without that 5 or that 3, without any translations. We're going to rewrite it in exponential form. And if we do that, we get x equals 3 to the power of y. Again, with logs, we're going to pick, this is the parent function, so we can pick 5 points centered around the origin, so negative 2, negative 1, 0, 1, and 2, and plug them in for y. And if we do that, we get 3 to the power of negative 2 is 1/9, 3 to the power of negative 1 is 1/3, 3 to the power of 0 is 1, 3 to the power of 1 is 3, and 3 to the power of 2 is 9. So we found our xy table. Using this xy table, we can actually find the xy table of the translated function, which we are actually asked to graph. So we're not asked to graph this, we're asked to graph the translated function. If we look at the translated function, like we said, in this set of parentheses, h is negative, meaning h is actually a positive number, it's 5. If this is x minus some number, we're moving to the right. If it's x plus some number, we're moving to the left. Because it's minus 5, we're actually moving right 5 units, so plus 5. So we're going to add 5 to all the x coordinates we found for the parent function. If we look at k, it's plus 3, which is pretty straightforward. K is a positive number. We're actually going to move up. So if k is a positive number, we're moving up. If it's negative, we're moving down. So we're going to move up, and in order to show that, we're going to add 3 to each of our y coordinates of the parent function. So if we add 5 to 1/9, we get 5 and 1/9. If we add 5 to 1/3, we get 5 and 1/3. If we add 5 to 1, we get 6. 5 plus 3 is 8, and 5 plus 9 is 14. Same thing with the y coordinates. Negative 2 plus 3 is 1, negative 1 plus 3 is 2, 0 plus 3 is 3, 1 plus 3 is 4, and 2 plus 3 is 5. After we find that, we need to identify what the domain and range is. As you can see, there's going to be a vertical asymptote, and as on the x coordinates, if you look at them, they're approaching 5. See how when you get to the number, integer value, 5 at least, you get fractions. So this is a mixed number, and these fractions are getting smaller and smaller, but you're going to approach 5, but you're never going to be equal to 5 or go to the left of 5. So you're never going to go to 4 or 3 or 2 or anything like that. That's where the asymptote is. So the asymptote's at x equals 5, meaning the domain continues from 5 to infinity, not including 5. That's why we have a parenthesis here. And the range, as you can see, is just infinite, as it's always from negative infinity to positive infinity for all logs. If we look at the graph, this is actually the curve. I didn't include this 14,5 point because that just doesn't fall on the axis, the x-axis. That's just too high. So I just included the first 4 points, plotted them, and then connected them, and then you can see that the asymptote is at x equals 5. So that's that problem for us. Let's look at problem number 3. We're going to be writing in exponential form. So we're writing each equation in exponential form. The equation is given in logarithmic form. So here's the first one. We're given log base 7 of 16,807 equals 5. How do we write this in exponential form? Hopefully you remember that e that we showed you. So if I draw that e, I start with 7, I draw the curve here, I touch 5, and then I touch 16,807 last. Since I touch 7 first, 7 is going to be the base. Then I come around, I touch 5. 5 is going to be the exponent, then we're going to draw an equal sign, and then 16,807 is going to go on the right side. So if we raise 7 to the power of 5, it's equal to 16,807. That's pretty much what this log is saying, and this is written in exponential form. So remember, we're sketching that E for exponential. It stands for exponential. Now we have a fraction. So this is log base 3 of 1/9 equals -2. We can sketch that E again. First we start with the 3. We're touching the 3, drawing the curve, touching -2, and then ending with 1/9. So what does that mean? Since we touched 3 first, it's going to be the base. So that's why we have 3 first. Then we touch -2. That's going to be the exponent we raised the base to. So 3 to the power of -2. Then we're going to write our equal sign, and then we touch 1/9 last. So it's going on the right of the equal sign. So 3 to the power of -2 is equal to 1/9. That's pretty much what this log is saying. So that's writing in exponential form, pretty straightforward. You can also switch from exponential to logarithmic form, but you're probably pretty familiar with that. In problem number 4, we're going to look at inverses. So in this, we're going to find the inverse for each function. Here's our first function. It's a log function. Y equals log base 2 of 4x. Keep in mind when we're finding the inverses of log functions, we're really trying to find exponential functions because they are the inverse, our opposite. So what we're going to do when we find inverses is first, we're going to switch the positions of x and y, and then we're going to solve for y. In this case, the first step we're going to do is rewrite this in exponential form just so it's easier to work with. If we rewrite this in exponential form, we get 2 to the power y equals 4x. That's written in exponential form. Now we're going to swap the positions of x and y, so we're going to rewrite that as 2 to the power of x equals 4y. Now we're trying to solve for y, so getting y by itself. In order to do that, we have to divide both sides by 4. So if we divide both sides by 4, we get 2 to the power x divided by 4 is equal to y. And then in order to simplify this, what we can do is we know 4 is a perfect square. 4 is equal to 2 squared. So we can rewrite 4 as 2 squared. So we get 2 to the power x over 2 squared equals y. And the reason we're doing this is so that we can use exponent rules. When you have bases, the same base with different that are raised to different exponents divided by each other, what you can do is simplify that fraction. In this case, this is 2 to the power x divided by 2 squared. You can simplify that fraction because the bases are same by just subtracting the exponents from each other. Just as if we had a multiplication sign here, what we could do is we could just add the exponents together. So if this was 2 to the power x times 2 squared, we can actually add the exponents and we would get 2 to the power of x plus 2. However, in this case, since we're dividing, we're doing the opposite. We can actually subtract the exponents, and that's how we get the exponential function y equals 2 to the power of x minus 2. Our next problem is going to be y equals log of x minus 6. So you can hopefully tell that since there is no base shown here, it's actually a base 10. So this is a common log. Since we know there's an imaginary 10 here, we know that the base is 10. And if we rewrite this in exponential form, we get 10 to the power of y equals x minus 6. Now we need to swap where x and y are. And if we do that, we can rewrite this as 10 to the power of x equals y minus 6. And to get y by itself, we're just adding 6 to both sides, and we get y equals 10 to the power of x plus 6. So pretty straightforward. And here's our last problem, number 5. It's going to be a special case. What is the difference between the following? And it's really important that you realize that even though these two logs look very similar, one has a set of parentheses and one doesn't. And the set of parentheses is very important. Oftentimes on assessments, teachers can actually, it's not like they're out to get you. They're never out to get it. They're always there to help us. But teachers might test your knowledge by throwing in the parentheses in one problem and then not throwing in the parentheses in the other problem, but the logs look almost the same. So that's the case here. You can see here we have y equals log of x and then minus 5. So log x minus 5. And then here we have y equals log of x minus 5. So there's a set of parentheses here. there are no parentheses here. So what is the difference between these two? Well, we can show the difference by finding the inverse. In order to find the inverse, we can first write this in exponential form. But before we even jump to that, what we have to do is we need to add 5 to both sides, because we have to add 5 to the left side so that we can take 10, raise it to whatever expressions on the left side, and set that equal to x. So what we're going to do is we're going to add 5 to both sides, because it's not in a set of parentheses with x, it's actually just dangling out here. So we add it to both sides, we add it to both sides, y plus 5 equals log of x, because minus 5 plus 5 cancels out. And then what we're going to do is, what I like to do is I just like to write the 10, base 10. So I write y plus 5 equals 10 equals log base 10 of x, just so I remind myself there's a common log there. Then we're going to write an exponential form, so we're going to raise 10 to whatever's on this side of the equation, so 10 to the power of y plus 5, and we're going to set that equal to x. And then finally, we're going to switch the positions of x and y. We get y equals 10 to the power of x plus 5. Y is by itself on one side of the equation, so we've actually solved for y, and we've switched the positions of x and y in one step. So this is the answer you would get if you had no set of parentheses. Now let's look at the answer you get if you had a set of parentheses. So since x minus 5 is in a set of parentheses, we can't just add 5 to both sides. It's almost like locked in a box with x, if you want to think of it that way. So we can't do what we did in the last problem. Instead, we can just jump into writing it as a common log. So y equals log base 10 of x minus 5. Afterwards, we can raise 10 to the power of y if we rewrite this in exponential form and set that equal to x minus 5. Now we swap the positions of x and y, and we get 10 to the power of x is equal to y minus 5. And finally, to solve for y, we're adding 5 to both sides, and we get y equals 10 to the power x plus 5. As you can see, the answers look slightly different. They're both exponential functions. However, the x plus 5 is all in the exponent up here when you don't have parentheses in the original log. But if you do have parentheses in the original log, you have 10 raised to the power of x, and then you have that plus 5 outside. It's not included in the exponent. So that's the difference I want to make sure you all notice. That's all I have for you today. I hope you enjoyed that video. If you did, please like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. Please also check out our website and our Gmail when you get a chance. Thank you, and I'll see you in the next video. Bye!